So thank you very much for the invitation. That's actually my first time in Russia and my first time to this conference, so I'm really eager to discovering both of them. And so today I'm going to talk about brain-computer interface, and in particular I'm going to talk about mental imagery brain-computer interface, MI-BCI, which are types of BCI in which users control the BCI system by imagining mental tasks. So for instance, they are imagining a rotation of a geometric figure, they can imagine mental mathematics, or imagining hand movements, for instance. And as many of you probably know in this audience, this is a type of BCI, MI-BCI, which is very promising for many applications. For instance, they can be used for assistive technology to enable a paralyzed user to control a wheelchair, for instance, to make a wheelchair turn left or right by imagining left or right hand movement. It can be used also for entertainment, to interact with video games or virtual reality environments, like in this video in which someone can walk in the virtual environment by imagining foot movements. Or more recently, it can be used for post-stroke rehabilitation for people who are paralyzed. The BCI can be used to detect movement intention, to guide the user to involve the damaged brain area due to the stroke and help them to recover. So this is a very promising technology. However, so far, BCI are still kind of unreliable. They make a lot of mistakes. They recognize the wrong commands sometimes from the user. And there is quite a number of users who cannot use the BCI system at all. So now, one of the big challenges of the BCI community is actually to make these BCI systems, MI-BCI in particular, but also BCI in general, to make them more reliable, that they can more robustly decode the commands from the user. So one way of doing that is actually to work on the machine, trying to develop better signal processing, better machine learning algorithms to robustly decode from brain signals, from EEG signals, what mental command the user wants to send. And there's actually a lot of research in this area. But another very important point, which I think is also a key element, is also to work on the user side. Because actually we know that controlling a BCI system is a skill that needs to be learned. The more you practice, the better you get. So if you want to really have a reliable BCI systems, you need not only good signal processing and good machine learning, but you need a good trained user who can produce clean, clear, and distinct brain activity patterns. So to do that, that means we need to train our user properly, and we need to provide them with proper feedback and proper training tasks so that they can learn efficiently and effectively how to control a BCI system. So far, that's how this training is done. You probably have seen that in many places. Typically, you have this kind of bar feedback in which the user is imagining, for instance, left or right hand movement, and you will see a bar moving left or right to tell him whether the BCI system has recognized a left or right hand movement. And actually, in the last few years, we actually show that this type of training tasks that are used in most BCI systems is actually suboptimal. It's suboptimal from a theoretical point of view because this type of training actually does not satisfy guidelines for efficient training that comes from educational psychology, from instructional design, or from theory of human learnings. But it's also practically suboptimal because actually if you use this type of feedback to train users to do something else, to learn something else than BCI, for instance, to learn simple motor tasks, several users will actually fail to learn this task due to the poor feedback that actually we provide them. So that means that actually the way we train our users so far is actually suboptimal. And so that means that we need to do better. We need to make this training optimal. And to do that, we need to understand the BCI training process. We need to understand it and we need to model it. And if we have these types of models, then we can use these models to provide an optimal training to our users. That's what we are trying to do now in our lab. And in particular, we are trying to understand the process and to model it. It means we try to identify which factors are going to influence the BCI performance and the BCI user learning. So we are looking at different types of factors. For instance, we are looking at what's the influence of the user profile on BCI performance and BCI user learning. For instance, what's the influence of the user traits, for instance, their personality, on their cognitive abilities. What's the influence of the user mental states, for instance, their frustration, their motivation, their attention, or what's the influence of the user BCI skills. But we are not only looking at the influence of the user themselves, but we are also looking at the influence of the machine side. So what's the influence of the EEG signal processing tools that we use on how users learn to control the BCI system? And what's the influence of the training task and the feedback we give our user to train them to control the BCI system? So we want to look at the influence of the user, the influence of the machine, but also all of this actually takes place in a specific environment, so we also want to find out the influence of the environment, for instance, the influence of the experimenters, the care person, or even the place in which the BCI system is used. So So if we can identify how all these factors influence BCI performance, BCI learning, and how they interact with each other, then we can build models that can be used to optimize the design of the BCI system and the way we train our user. We can optimize the EEG signal processing, the training task of the feedback, to give an optimal training for each user and hopefully obtain a BCI that is finally reliable. So in that talk, I'm going to show you some of the work we do at these different levels to understand and model BCI user training. So let's start with trying to understand the influence of the user profile on BCI performance and learning. So to start to do that, we first look at what's the influence of the user traits. That is, what's the influence of the user stable characteristics on BCI performance. So to answer these questions, we run a number of experiments in which we train our user to learn to control a BCI system across multiple days, across multiple sessions. And notably this type of BCI that you see here on this picture, in which the user had to learn to control a BCI in which that we imagine left-hand movement, or to do mental subtraction, or to do rotation of a geometric figure, to control 3 different commands using the BCI. So we train our users, and we also ask them to fill in some questionnaires from psychology to learn about their profile, their personality, and their cognitive abilities. So we actually run multiple experiments like that, and by combining the results of these experiments with the literature in BCI, we actually managed to identify 3 main families of factors that do have an influence on BCI performance. So one of them is spatial abilities. That is the ability to create, manipulate, and transform mental images. So that's something that you can measure using a test called the mental rotation task. So actually you show people a geometric figure, the one you see on the left here, and you show them on the right 4 other figures. And you ask them, okay, among these 4 figures, 2 of them are the same one as the one of the left, but rotated. So if you're good at correctly identifying which of these 2 figures are the same one as the one on the left, most likely you will have better performance at BCI control. Another trait family is attention. So people who have usually higher attentional capabilities or who pay more attention to the BCI system and to the training task will usually have better performance as BCI control. And finally, the last family of factor that we identified is the relationship with technology. For users who are anxious with technology or do not feel comfortable with technology or do not feel in control with the technology, those types of users, usually they would have lower performance with BCI systems. So this research actually enabled us to identify some types of conceptual model of BCI control and to identify some relationship between some factors and BCI performance. But that's only conceptual models. Now we are trying to go further and to really build computational models to really find out what's the relationships between these different factors and exactly how well they can predict performance with BCI systems. So to answer these questions, now we are trying to build these computational models and across multiple experiments to see really if we can predict the performance of our user based on their traits of these different users. So to do that, we actually gathered data from multiple experiments. So we gathered data from 43 subjects who trained to use a BCI system between 3 sessions to 6 sessions, so for a total of 186 sessions. And so they all learned to use the BCI I mentioned before, based on left-hand imaging movement, mental subtraction, and mental rotation. And we wanted to see whether we can predict the performance based only on the traits of the users. So to do that, we had access to all these different characteristics that we measured using psychological questionnaires. So we had the spatial abilities of the user measured using the mental rotation test I've showed before. We have the personality of the user measured using the 16-pair-5 questionnaires that come from psychology. And we also had information on the learning style of the user using the learning style inventory. And so all these features, we gave that to a lasso algorithm, a sparse linear regression. That is a linear regression that we select a few variables to predict target variables using linear regression. And in our case, what we want to predict is the mean BCI performance across the different sessions that the user used the BCI systems. So we want to predict this performance. So we trained these lasso algorithms on data from multiple subjects, and we apply that on a new subject to see if we can predict the performance of this user using only the measure of the user traits. So we use leave one out subject cross-validation. So we try to do that on different groups of subjects. So we try to perform that for each of our 3 experiments separately, or on different combination of the different experiments for which the sessions were matching. And so across these 6 different groups that we had, we could predict performances better than chance, but only in one of these groups for the first experiments, for the experiments for which we had the highest number of sessions, 6 sessions. For that experiment, you can see here the variables that were most often selected by the algorithm across the cross-validation folds. And you can see by using a mental rotation score, tension, which is a measure of anxiety, and self-reliance, a measure of autonomy of our user, whether they want to work alone or in group, we can predict the performance better than chance. So you see here the real performance and the predicted performance, and you can see that they are quite highly correlated. However, you can predict the performance better than chance only for that experiment. For the 5 other ones, we cannot predict them better than chance, which tell us 2 things. First, probably to predict the performance, we need a large number of sessions because we predict the average performance across sessions. So by averaging across more sessions, we actually average out the within-user variabilities, which seems to be quite large. And also that means that definitely traits are probably not enough, and certainly not enough to predict the performance of users between users. So that means we need to model the influence of other factors and to consider the within-user variability as well. So we're actually working on that at the moment. So we're also trying to predict the within-user performance, so trying to predict the future performance of users from their traits and from their past performance. And interestingly, that's something that you can do better than chance across all experiments. So here we try to predict the performance at the second session from the traits of the user and the performance at the first session, and we can predict that better than chance. You can see here that the real and predicted performance, and they are also quite significantly correlated. And in that case, the variables that are important, the main ones are, again, mental rotation, but also vigilance, which is also a subfactor of anxiety, and the performance as the previous session. And by doing that, we can predict the performance of the next session. So globally, with these modeling experiments, we could show essentially that there are 2 main traits that seem to be quite important. So mental rotation that appeared in our 2 models, both between users and within users, and also the anxiety traits, because both tension that was found in the previous model and vigilance in this model, they are actually sub-factors of the anxiety global factor. So that's an important factor we need to consider when designing BCI systems. Now, if we want to estimate the within-user performance variability, we need to consider something else than the user traits. And in particular, we need to consider the user states and skills as well. So typically for BCI skills, usually what we consider as good BCI skill is good BCI classification performance. But actually, we showed recently, in the paper I showed here, that actually it's not a good measure of the user skills. Because this BCI classification accuracy, it depends on both the BCI skills, obviously, but also on the machine learning skills, on the classifier performance. So if you give a bad classifier to a good user, he will have bad performance, even if it's a good user. So we actually propose some new metrics that are independent of any classifier or any data calibration data. And we could show that by using these types of metrics, we can reveal very different learning profiles. So you see here in yellow, there's the classical classification accuracy, which depends on the classifier. So that's the performance average of our user across runs, and in that experiment, we don't see any learning for the user. But by using our new metrics that are independent of classifier, we can see that actually the user are learning something. It's just that the classifier didn't figure it out. So this means that we need to consider new metrics of user skills in BCI control. We are also interested in estimating the states of the user, because actually we know from psychology that in learning there's a number of mental states that are quite influential on the learning success. For instance, whether the user is paying attention to the task, about the mental workload, mental efforts that the user is putting on the task, or whether the user is actually curious about the task or not. So we are actually currently, I'm not going to enter into details now, but we are designing new protocols and new machine learning tools to estimate these different states from EEG signals. For instance, we could show that we can discriminate different types of attention from EEG signals or different workload levels. And now we are working on curiosity, and it seems we can also discriminate more or less some curiosity level from EEG signals. So our next step is then to monitor these states in real time from EEG signals, and then to see how they influence the success of learning. So let's move on to the next family of factors on the environment and the influence of the environment on BCI performance and learning. So about the influence of the environment, we actually looked at one specific influence, the influence of the experimenters themselves. Because actually we know that in other fields, the experimenters are known to have actually a strong influence on the results that they themselves obtain. In particular, there actually seems to be a strong effect on the influence of the gender of the experimenter on the obtained outcome depending on the gender of the participants. That's something that was observed, for instance, in education or in economy and in many fields. This can be due, for instance, to social expectation, to social pressure, or even to some attraction effects. And actually, recently, it was also observed in neurofeedback that there was some influence of the experimenters on the results of the experiments. So we wanted to see whether, also in BCI, the gender of the BCI experimenters could have an effect on the BCI user performance depending on the gender of the participants. So we ran an experiment to do that. So a first experiment in which we train users across just one session to learn a BCI based on left-hand imaging movement or right-hand imaging movement. And in that experiment, we had 6 different experimenters, 3 men, 3 women, and 60 different subjects, half of men and half of women. And each experimenters were training 5 men and 5 women to control the BCI systems. And we look at the performance across the different runs, depending on the gender of the participant and the gender of the experimenter. And actually, we observed some influence. Actually, we observed a significant interaction between the performance across runs and the gender of the participant and the experimenter. So it's significant, but it's a small effect, so nothing too big. But what it seems to show is actually, in general, subjects seems to do better with women experimenters. So actually, usually, men that you see in blue here, men have better performance when they are trained with women than when they are trained with men. And for women, actually, they start better when they train with men, but their performance decreases across times, but they learn better when they are trained with women. So it's quite an interesting result. So I need to mention I was one of the men experimenters, so it was not a good news for me that I had actually a bad influence on my subject, but that's how it is. So we're still not sure why it's the case, but in any case, there could be actually a number of confounding factors because we have not that many experimenters, but it seems to suggest that still experimenters do have an influence on the performance of their BCI users. So now let's move on to the last part, so the influence of the feedback on the performance of our users. So I'm going to show you two brief experiments, two series of experiments that we ran on the influence of the feedback on BCI performance. So for instance, we study different types of feedback modality. So typically feedback in BCI is visual. We also studied some vibrotactile feedback. So for instance, we designed these types of gloves that provide tactile feedback to our users, so vibration on the hands. And we could show that by using this feedback, actually users tend to obtain better performances in BCI than when they use only visual feedback. And especially actually if they are using a visually loaded environment, it actually reduces their visual load and so they have better performance. And we also studied that on a more longer term using this type of system in which we combine realistic visual feedback with 3D hands moving and tactile feedback on the hands. So that's the system we are developing for post-stroke rehabilitation with the hospital in Bordeaux. And so we tried that so far only on healthy users, but we could show that also across time, the tactile feedback in blue gets consistently better performances. So when you combine visual and tactile feedback, you get better performances as compared to visual feedback only. And you also observed quite an interesting result that we were not expecting is that if you start with visual feedback, you will get even better performances if you learn after visual plus tactile feedback, so than the opposite. So if you start with tactile feedback after, we're not sure yet why, but that was interesting. Another type of feedback we study is the influence of the perceived difficulty depending on the feedback that we provide our user. So we are studying biased feedback, that is feedback that makes users believe they are doing better or worse than what they are actually doing. So we studied that using this type of game, quite cute game in which users actually had to control a penguin. So they were making the penguin move left or right by imagining left or right hand movements, and the goal was to catch fishes on the left or on the right. And so actually we bias the feedback by sometimes making the penguin go closer to the fish or further away to the fish. If the user were not good enough, we'll help them to positively bias the feedback towards the fishes, and if they were too good, we'll make the penguin a bit further away from the fishes to make sure that the task is neither too boring because it's too easy, nor too difficult. Adaptive bias feedback, so we continuously adapt the bias, positive or negative, depending on the real-time performance of the user. We could improve their feeling of control, and they were feeling more in flow with the task, but that didn't change their actual performance. And when we were training with fixed positive bias, so always making them believe they were better than real, they will also improve their flow and the user experience, but it actually decreased their learning performance. And when we used fixed negative bias, so making them believe they are not as good as what they really are, they initially learn better, on the first session, but on the longer term, and actually they learn not as good because they probably decrease their motivation because it's too difficult for too long. So that brings me to, I have to finish, but that's my last slide. So what I want to say in that talk is that user training is really a key element for MI BCI if we want to obtain reliable brain-computer interface systems. And if we want to optimize this training, this user training, we need to understand this training and we need to model it. So in that talk, I've shown you some of the work we've been doing on that to identify the influence of the user traits, for instance, the user mental rotation score or the user anxiety. We're also working on providing new measure of states and skills, and we reveal the influence of the experimenters, of the feedback modality and bias on user performances. But obviously, that's just the beginning. There are many more factors we need to identify that we need to model, and when we have this full model, we can finally adapt the BCI training and adapt the signal processing to each user, depending on their profile and on their skills evolving with time. And so hopefully we'll have a good BCI in the end. Thank you very much for your attention.
Thank you. The question is the following. Maybe can you switch to the last video with Penguin?
Yes, this one.
You can see that the patient is moving his head to the left and to the right when the penguin moves. And as I know, it's a common problem that people learn to control such devices using artificial muscle movements, but not true brain signals. However, since it's not fundamental science but practical applications, I guess we don't care since patients have the results. But the question is following, why we should focus on brain-based devices and not on muscle or eye movement control devices, because they are much easier to learn. I guess the only patients who can't use them are locked patients. So two questions. What % of patients are true locked patients who need such devices? And for other people who can control eyes or muscles, what are benefits of brain power devices comparing to muscle or eye movement devices? Thank you.
Yeah, that's a very important question. So just to comment on this one, indeed, that specific video, actually I got the remark very often when I show that video, it's indeed moving the head. So we make sure the control is not based on muscle activity, so we are really focusing on sensory motor rhythm in that case, and checking the data to be sure it's not the case. But there's still a valid question. So what's the percentage of locked-in patient, or fully locked-in patient? It's very, very small. I don't know the exact figure. Probably some other speaker could mention that, but it's extremely small. So for them, definitely it's variable. But there are many other applications for which BCI could be useful and for which you don't have to be locked in. So I mentioned stroke rehabilitation. I'm sure that some other speaker, probably Sergio, you will mention that later this afternoon. That's an application in which BCI is really useful. And it needs to be based on brain activity, because for stroke rehabilitation based on BCI, the idea that you really guide the user to involve the damaged brain area, to tap on brain plasticity to help toward recovery. So you want the control to be based on brain signals. At least so far, that's the theory that's driving the whole system. For the other users who have maybe some paralysis but can control other muscles or eye movements, that's true that for the moment, most probably they don't need a BCI. So there are a lot of other assistive technology, maybe based on switch, on eye trackers, that would be more efficient than BCI, because clearly BCI, they work, but as I mentioned, they don't work well. So if we cannot make them more reliable for many applications, they won't be competitive with other assistive technology. So it all depends on how far we can push the technology to see if that can be used. And finally, I'm looking at Thorsten, because this is only BCI application for controlling something, but there are a lot of other applications that can be used in which BCI is used to monitor brain activity. And I'm sure Thorsten will tell you all about it later this morning. So I'm not going to mention more, but there are a lot of other applications than control for which BCI can be useful.
Thank you. Much needed work, actually, and very important, of course, in the context of BCI. So my question is, you're probably familiar with the work of Blankertz and Dickhaus, and I will also present later that when predicting BCI performance, you can also look not only at the performance measures as such, but also at the kind of resting state parameters. So do you combine it in your research, and how does it add to what you're showing?
So in the data I've shown, we are So for these predictors you mentioned, you need a long baseline recording. And so for those data, we don't have a long baseline recording for all our subjects. So we cannot do that on that specific database. But now we do record that for all our experiments. And definitely that's something we are going to use. And this new predictor seems to be quite robust as well. And so that's definitely some of the things we are looking at the moment as well. So predictors based on resting state activity. We're also looking at, I didn't mention that, but that's ongoing work, and the characteristics of the features we use for BCI control. So there's a lot of variability between the different types of features, the different type of spatial filter, the different types of classifier that we use to control the BCI system. And most probably this also have an influence on BCI performance and BCI learning. So we need to find out what's this influence. Actually, there are some studies that show that with machine learning, we get better initial performances, but on the longer term, simpler features and simpler classifier leads to better learning, probably because the system is easier to understand from the user point of view. So we need to understand exactly what's the influence of these different factors in the whole model.
Okay, thank you.
You're welcome.
This is Johannes from GTEC in Graz.
Hello.
I've seen some GTEC equipment here,
Yes.
so
Yeah.
thanks a lot for your very interesting talk. I'm actually very interested in the classifier architecture. So you already mentioned something about this, but could you briefly explain which classifiers you're using and why?
So it depends on the experiments. So most of the time, so far, we use common spatial pattern spatial filters. So we filter our data in some frequency band, relevant frequency bands, or sometimes optimize for the subject depending on the experiments. We then use spatial filter using CSP, and then most of the time LDA classifier. So most of the experiments I've shown, probably all of them, most of them were based on that. I'm not sure we'll still use that in the future. We have to find out. More recently, we trained the tetraplegic user to control the BCI system, and we used Riemannian geometry classifier, adaptive ones, and it was giving quite good results. And also because of the point I've just mentioned, I'm not actually. There's a debate. We recently discussed that at a workshop in France, but there's a debate on how complex the machine learning should be. Because we can have very advanced machine learning that are, from a pure machine point of view, the best, but are they really the best to give feedback to the user? Because the more complex your machine learning, the more complex your feedback, and so the more complex for the user is it to learn from that feedback. So there's probably a trade-off. I don't know what the trade-off is, but we are looking into that at the moment, so we might change that in the future.